Hey guys, and welcome to a video on green chemistry. So today we'll be going over two main things. So firstly going over what actually is green chemistry in the first place, and then we're going to be going over some of the history and where green chemistry came about, and then going over 12 concepts that kind of underpin this concept of green chemistry. You can apply these three things to kind of answer any question on green chemistry. In the second part, we'll be talking about the calculation of atom economy. It's relatively straightforward compared to all the other calculations you've done, but it's pretty integral that you understand that for this concept of green chemistry. So before we begin, we'll start with a brief discussion on green chemistry and cleaning up pollution. So we apply the concepts of green chemistry when we're actually making chemical products, such as ammonia in the Haber process, for example. Green chemistry minimizes the hazard substances at the source. So we're trying to make the process of making the chemical product as green as possible. So we're minimizing the amount of hazardous reagents, solvents, and products that we actually use and make, right? The counter of that is cleaning up pollution. So with cleaning up pollution, we kind of accept that a process such as the Haber process is going to produce a lot of carbon dioxide, is going to produce a lot of sulfur dioxide, and then we deal with the repercussions of that after. So green chemistry is a source of source mediation, whereas cleaning up pollution relies on remediation, right? So now that you've understood that, there are some key principles in green chemistry. So we're basically looking at a chemical process. So again, to use the example of the Haber process, and number one, preventing pollution at the molecular level. So at each step of the chemical process, we're trying to see about how we can make the process as clean as green as possible. Now there's a framework in which we can do that, and we'll go over that in the next couple of slides, but that's just one of the key principles. We can apply this philosophy to all areas of chemistry. So I keep bringing up the concepts of the Haber process. We can apply this thing throughout all of chemistry and any molecular processes. We apply scientific solutions to real-world environmental problems to make these chemical processes as viable in the future as possible. And in doing so, we reduce the negative impacts on the chemical product and processes on human health and the environment right now and into the future as well, because ultimately we're eliminating the amount of hazardous substances that we produce and process. So with green chemistry, it's important that you understand a little bit of context with it. So to stop creating pollution in the first place, it was actually America that proposed the concept of green chemistry, and it officially politicized green chemistry through the Federal Pollution Prevention Act in the 1990s, and that's actually quite important for you to remember. So you can think of this Federal Pollution Prevention Act as having two significant sections. So in section 1, we're kind of exploring the crux of green chemistry and looking at the definitions of certain things and the agenda behind it. And in section 2, the Act gives us a framework for how we can actually apply the concepts of green chemistry in the first place, right? So we'll start with section 1. So I'll give you a little bit of an example. So in the 1990s, the demand for chemical products such as ammonia and the Haber process was ever increasing, right? As the demand increased, you need to meet that demand and increase the supply, right? So you need to make more of something. And if you make more of the chemical product, inevitably, you're going to make more waste and toxic substances as well. Now, there's two ways we can deal with this, right? We discussed this in the previous slide. In cleaning up the pollution kind of way, we fundamentally accept that a chemical process isn't great, and we just deal with the repercussions. We deal with the toxic substances that we produce, right? However, this new age of thinking of green chemistry kind of proposes something we know as source reduction, right? So the definition of source reduction is the reduction of the amount of hazardous substance, pollutant, or contaminant entering any waste stream or the environment in general, right? Now, the aim of source reduction as a result of green chemistry, so source reduction is a key word, is to reduce the hazards to overall improve public health and environmental outcomes. So with Section 2 of the Federal Pollution Prevention Act, it kind of gives us a hierarchy for how we can accomplish this concept of green chemistry. So it's mandated by Congress in the United States of America that pollution should be prevented or reduced at the source, so in accordance with source reduction whenever feasible. And then if we can't do that, then number 2, treating these chemicals or toxic substances. So whenever I say chemical, or I mean chemical hazards. So treating these chemical hazards, if you like, to render them less hazardous before we dispose of them. And then at the very last, if it's completely unfeasible, right, disposing of these untreated chemicals safely, right? So not just into waste bodies of water that's going to have significant impacts on ecosystems, right? And we'll go over these concepts in a little more detail. So with your Year 12 exams, it's pretty important that you know this hierarchy quite well. So always remember you're trying to prioritize source reduction before anything. Number 2 and 3 is just if you can't or it's less feasible to do so, you move down the hierarchy, for example. So with source reduction, there are a couple of key points that we need to go over. So the whole premise of it is highlighted in the first 2 dot points. So overall, we need to design chemical products and synthesis pathways that have the main impact of reducing the impacts to human health overall and environments and ecosystems, right? But we've been talking about this for a while, but how do we actually do this and implement this in the first place? There are a couple ways, and I recommend you actually know these dot points pretty well. So we can design a synthesis or process with reduced or even no chemical waste. So what could this look like, right? This could potentially look like a single one-step reaction where you have the reactants reacting to form the product. No multi-step process that can potentially cause a lot of chemical waste, just one nice chemical reaction. Unfortunately, if it were that easy, we'd be doing it. There's a reason why we don't. The yield on these single-step reactions is usually kind of crappy. So we tend to utilize these multi-synthesis step pathways to overall increase the yield, and then we kind of clean up the pollution that we produce. However, in the future, if we have, say, a special catalyst or an enzyme for a particular reaction that we can use that makes these single-step reactions pretty worth it, then that's definitely something to explore. Now, with the concept of green chemistry, we've been talking about chemical waste a lot, but it doesn't just refer to chemical waste. We also need to look at synthesis and processes that use less energy and less water, right? Another point that we need to address is our reactants. Firstly, our reactants being from renewable resources or waste products. So ideally, the waste that we do produce, we want to make that into more reactants. However, that's really hard. Another alternative is having reactants that are renewable resources in the first place, right? Conversely, we also need to make chemical products that are able to be recycled and reused. And a good example of that that you can use your exams is cork and the wine industry, right? So as you may be well aware that wine used to have corks on it. However, this ultimately wasn't that recyclable. So there's just been a hush-hush kind of gentleman's agreement within the wine industry to have a screw-on cap instead of that cork. And that screw-on cap is made of aluminium, which is a lot more recyclable than the cork, which was ultimately contributing to landfill, right? So the last 2 dot points kind of tie hand in hand. So we need to have reactants that are from renewable resources or from waste products. And we need to actually produce a product that is recyclable, right? Or is renewable in the first place. So for you as a Year 12 chemistry student, what does this actually look like? So when you're answering questions, the first thing you need to do is you need to highlight the context of green chemistry. So looking at what the actual premise of it is, why we do it, talking about cleaning up pollution versus green chemistry, talking about the Federal Pollution Prevention Act, then the hierarchy really quickly, don't talk about all these dot points, and then you want to go into these 12 concepts involved in green chemistry. Now it sounds like a lot. We do have some great flashcards on these 12 concepts. However, it's important when you're constructing an answer that you do apply these concepts to whatever stimulus you're given. So we'll go over these 12 concepts involved in green chemistry quite quickly because they are relatively straightforward. So with concept number 1, it's kind of in the name. So we're preventing the amount of waste that we produce If we do that, there's nothing to clean up at the end. That's kind of the crux of it. With number 2, it's about maximizing atom economy. Now, I don't want you to worry about what this is just yet. We'll be going over this concept in the next slide because these are a lot of the crux of the calculations that you need to do in green chemistry. So just hold point number 2 in your mind just for 1 second. So you can kind of group points number 3 and 4 in your head. So the overall point of these 2 points is that we're trying to, number 1, produce a better chemical synthesis pathway that produces less chemical waste. And number 2, we're trying to produce more recyclable chemicals in the first place, right? So if you can imagine, if we make a super green chemical process, however, our product at the end is incredibly toxic, that kind of defeats the whole point of green chemistry. So our aims in point number 3 and 4 combined is a great chemical process that is green, and number 4, a product that is also green and also recyclable. In a lot of these chemical processes, we're going to be using auxiliary substances such as separating agents or solvents, for example, right? That's something you need to take account into your green chemistry. So you can't just forget these solvents and these auxiliary compounds such as your separating agents. Every substance that you use in your chemical synthesis pathway, you need to take into account in this conversation of green chemistry. Point number 7, we did touch on in the previous slide. So we're trying to move away from non-renewable resources such as fossil fuels, for example, to produce a chemical product such as natural gas. We're trying to use more renewable feedstock or reactants such as sugarcane to produce a more renewable substance such as ethanol, for example. So point number 8 kind of touches on that concept of using a one nice clean single cut reaction. So we're trying to avoid the amount of other substances or these chemical derivatives that we produce. So chemical derivatives have had to go through a previous process and then they react and make more product, which then reacts and makes another product, which then reacts and then makes your final product, for example, right? So we're trying to avoid the amount of chemical derivatives that we're producing. Ideally, as in the previous slide I said, we'd have a nice clean cut reaction. However, due to obvious reasons, that isn't quite as easy as it sounds. So number 9 is quite straightforward. So we need to make sure we use catalyst as much as we can. So with the catalyst, we overall decrease the amount of activation energy required by the molecules to actually participate in the reaction. Overall, more molecules will be able to participate in the reaction, so we can increase the reaction rate by keeping the reaction temperature and the pressure down. So overall, this will make the whole process a lot more greener because the whole reaction can operate at a lower temperature and pressure, both of which are great for green chemistry. So the whole premise of point number 10 was we're trying to make chemical products that don't build up to toxic concentrations in the environment. The crux of point number 10 is that we need to make chemical products that are biodegradable. So once they're in the environment, they quickly decay over time, or they're even recyclable, for example. So points number 11, 12, you can kind of pair in your head. So with 11, it's a nice easy mark. So basically, a good way for any chemical synthesis pathway to become more green is for the operators to monitor the process in real time. So having a look at how much feedstock we're actually feeding into the process, how much product we're getting, and ultimately how much waste we're getting. So having data on all of those things is quite important. Number 12 is minimizing the potential for accidents. So accidents such as explosion, fires, releases to the environment such as an oil spill. So you can talk about all these 3 things. Our chemical synthesis pathway can ultimately be modified to minimize this potential for accidents. An example of this would be, say, an explosion, for example, right? If we're operating at very high temperatures and very high pressures, the chance of an explosion would be pretty high, right? We can minimize this chance of explosion by having a catalyst, right? With the catalyst, we can operate the chemical synthesis pathway at much lower temperatures and pressures, and thus the overall potential of an explosion kind of goes down. So as you can see, you can apply this framework. So you'll get a stimulus, for example. So you get a chemical synthesis pathway, and then you'll be asked to talk about it. You can apply these 12 concepts to pretty much anything, and you can make that process a lot more green. So one of the key concepts in these 12 concepts of green chemistry was this overarching theme of atom economy, and that was especially pertinent in point number 2, right? Our next kind of discussion will be, firstly, what actually is atom economy in the first place, and then secondly, how do we actually calculate the atom economy of a chemical synthesis process. So this concept of atom economy refers to how much of the reactant atoms actually form the final product, right? And the higher the atom economy, the lower the amount of waste products that are formed, because the higher the atom economy, the more of the reactant atoms are used to make the final product. So you don't have any leftover atoms to actually make any waste products, right? To give you a more practical example of how this works is, if you're a chemist, right, would you rather start off with small building blocks and produce your final product, which is a little larger, and you have a small kind of waste? Or would you rather have a large kind of starting point, and you can break it up into your product? However, this time you have a huge amount of waste, right? Huge amount of waste. Obviously, you'd rather start with this up here. And this brings me to the point of the ideal atom economy being 100%, or a reaction where all of the atoms in your reactant are used to make your product. And ideally, there's no waste. So I've got 2 examples in the following slides for how we calculate atom economy. The actual math of it isn't too hard. It's more so just understanding what you're calculating in the first place. So with the first example, we're looking at a relatively large molecule being broken apart to form a product, which is calcium oxide. So if you can recall my diagram from not so long ago. In the second slide, we have 2 smaller molecules combining to form a final product. And we're going to explore how both of these chemical processes have a difference in atom economy. The overall equation is this to calculate atom economy. It's the molecular mass of the desired product, so the molecular mass, divided by the sum of the molecular masses of the reactants. And you need a percentage, so it's times 100%. So now we'll go over how to actually calculate the atom economy for this reaction here. So obviously in this reaction, calcium carbonate is being broken up to form calcium oxide and carbon dioxide gas. Our product of interest is calcium oxide, and our initial reactant is calcium carbonate. So I'll write that. So our reactant is calcium carbonate, and our product is calcium oxide. Okay, so firstly, if we look at the formula, in the numerator, we want the molecular mass of the desired product, right? So the desired product is calcium oxide. You can very well find the molecular mass of calcium and oxygen, which is 40.1 for calcium and 16 for oxygen. If you add those two, the molecular mass for calcium oxide is 56.1. So on your numerator, you're going to get 56.1. On your denominator, we want the sum of the molecular masses of the reactants, right? So with this reaction, it's relatively easy. We only have one reactant, so we need to find the mass of calcium carbonate. So we need the masses of calcium, 1 carbon, and 3 oxygens respectively. If you add that up, you get a total of 100.11. If you express this as a percentage, you get 56% once you put all your values in. So what does this 56% actually tell you? So it's telling you that 56% of the atoms contained in calcium carbonate are being used to form calcium oxide. The other percentage is the waste, which is carbon dioxide in this case. So when you're talking about this process, you could calculate the atom economy in an answer and then show that maybe using another synthesis process, using maybe like 2 smaller molecules, we could improve the atom economy and get it closer to that 100% ideal. A bit of a different example in the second one here. We're using smaller reactants to form a larger product, unlike the first example that we had. You may recognize this equation as the equation for the Haber process, in which we're using nitrogen and hydrogen to make ammonia, right? Same process as always. So firstly, we're going to be dissecting this equation firstly. So looking at this equation and then identifying our products. So obviously, our products, we just have one. It's 2 moles of ammonia, right? And our reactants are nitrogen and 3 moles of hydrogen gas, right? Let's work with the formula that we have. So atom economy, like I said, is the molecular mass of the desired product divided by the sum of the molecular masses of the reactants times 100%. So as always, we can start with the top. So the molecular mass of the desired product. Our desired product is ammonia. If you look at your periodic table, ammonia has 1 nitrogen and 3 hydrogen, right? Nitrogen has a molecular mass of 14. Hydrogen has a molecular mass of 1.008. You have 3 of the hydrogen, so you need to multiply 3 of those 1.008s. You add those two together, and you should get a number. However, you have 2 of those ammonias that you produce, right? So you have 2 of these ammonias. So you need to multiply all of this by 2. And once you do that, you should get 34.048. So your numerator is going to be 34.048. So we'll do the exact same for our reactants now, and I'll draw that again. So our reactants, we have nitrogen and 3 moles of hydrogen, right? So again, if we look at our formula, the denominator says that the sum of the molecular masses of the reactants is what we require. So nitrogen, or the divalent nitrogen, has a molecular mass of 14 times 2, right? Hydrogen, H2, has a molecular mass of 2 times 1.008. However, in this reaction, you use 3 moles of hydrogen. You use 3 of them. So you need to multiply all of this by 3. Once you put that into your calculator, you should get 34.048. Now you might be thinking, why do we multiply? So there's a 2 here, there's a 3 here. Why do we bother multiplying the 3 and why do we bother multiplying the 2, right? So basically, why do we, the coefficient in front of the molecule, why do we multiply it when we're actually calculating the atom economy? That actually comes down to, if you think about it, the definition of atom economy. So let's revise that. Atom economy is a reflection or a percentage of how many atoms originally present in the reactants are used to make the final product, right? If we don't multiply it by 3 and by 2 respectively, we're not taking into account all of the atoms that were initially present if we don't multiply it by 3, or we're not taking into account all of the atoms that are finally present that are producing the ammonia, right? So we're going to be missing some atoms. So we need to take into account all of the atoms. One other thing that I wanted to bring into focus is notice how we didn't calculate the molecular mass of any waste products such as carbon dioxide. All we're looking at is the reactants and the final product. The reactants and the final product, that's all we need. Once you put that into your equation, you get 34.048 divided by 34.048 times 100%. If you put that into your calculator, you'll get 100%. What that tells you is this equation has a atom economy of 100%, or 100% of the atoms that are present in the original reactants are being used to make the final product. So this is a very good reaction. So this concludes our discussion on green chemistry. So when you're answering questions, this is just a nice quick framework to use.